This is Pete LaBeouf for Chapter 22 Video Reassessment, and I'm doing problem number 31 out of the white textbook, and I'm really just using that as a base for what I actually wanted to get to. But this is actually a pretty good problem because it's a kind of redemption for me having to do another sunlight problem. But for this one, we are given, it's asking us, what is the power that hits a specific spot on the earth from the specific power of sunlight that hits the earth on a specific spot in a specific area, which that area is 0.75 meters squared, and then the power that is radiated by the sun is 3.9 times 10 to the 26th watts, and then the radius from the sun to the earth is 1.5 times 10 to the 11th meters, and the earth is at a 27 degrees axis of rotation, so that means the earth is from here to here is 27 degrees. And for this one, we use a simple power equation just to figure out what the power is that's hitting there. So we take the cosine of the angle, the power that is radiated from the sun, and then the area that the sun's actually hitting, and then we do that over the area of the total area from here to here, which is 4 pi times 1.5 times 10 to the meter squared, which all comes out to be 920 watts, and that's the amount of power that is actually hitting that one specific spot on Earth. Now, what I went and did after this is I wanted to see, given that power, what is the intensity and the frequency of the light that is hitting that area of the planet. So to find the intensity, we simply take the power that is radiated from the sun and then divide that by the area that is from the sun. So in other words, just doing the same kind of process as we did here. Only thing is now we're looking for intensity, not the power. So that means we don't need the angle. So that came out to be 4.54 times 10 to the 37th watts per meter, which I should probably write that in. Meter squared. And then using that, I use this equation, which is it's used to find using frequency, the number of photons, the number of lights. So this one I just used 1, since they're just looking for how many times one photon of light hits Earth. I just kind of approximated that. And then we use Planck's constant times divided by the area divided by the time. And since it takes about 8 minutes for one photon of light to actually go all the way from the sun to the earth, I converted that to seconds, which is around 480 seconds, which might be different in real life depending on a few different things. But so our frequency, after moving this frequency around, their frequency there is in the middle. After moving that around, I come up with this equation, which is F is equal to intensity times area times time divided by the number of photons divided by Planck's constant. Ugh. And then that gives me a final frequency of 249,230.77 hertz, that's really, if you want to convert that decimals, that'd be really, really freaking loud. So it's a good thing that there's no air between us and the sun. Otherwise, I'm pretty sure we'd all be deaf, and it would not be a good time. So, well, considering that the sun is literally nothing but nuclear fusion going on, yeah, that should be pretty loud. All right, over and out.